So now I will talk about functional derivatives and also about the Hadamard product, the 2 points that were already discussed by Eric. So the first point, so this is a work that was essentially started by Kasia Reisner, who is a mathematical physicist in her PhD thesis. And we did this work with a number of mathematicians, Johan Dabrowski, Viet Nguyen Dang, Camille Laurent-Gingoux, and Frédéric Hélin. So I was very interested in this problem of functional derivatives because they are very often used in many-body physics. For instance, you define your green function as the functional derivative of the partition function with respect to sources, which are anti-commuting, but and you define from the non-interacting partition function, which is here, you can define the interacting one, again, by using functional derivatives with respect to these sources. So the problem that we had was how to give a mathematical meaning to functional derivatives. So there is a very general way to define the differential, which was given by Gatto at the beginning of the 20th century. And the idea is that if you have a function from a space E to a space F, you say that you have a derivative at point U in the direction of V if the following limit exists. So you take f of u plus tv, you subtract f of u, you divide by t, and you take the limit. If this limit exists, then you say that you have a Gatto differential. It's a very standard thing, but if you want to do it in a more general way to allow you to make functional derivatives with respect to functions or with respect to green functions, then you have to be more general than what you do usually. You see that you need the structure of a vector space because you write u plus tv, so there's a sum, and there is multiplication by a scalar, so you need the vector space in E and in F. And then what you need also is a limit, so you need a topology on these two spaces. So the minimum mathematical framework is that of topological vector spaces. Now there are two kinds of common topological vector spaces. There are known vector spaces, the Banach spaces, which are complete norm vector spaces, where you have only one norm. And the one which is usually used in quantum mechanics is Hilbert spaces, where the norm is defined from the scalar product. But in that case, when you want to make derivatives with respect to smooth functions, for instance, you cannot work with only one norm, and you have to work with an infinite number of semi-norms. So a semi-norm is like a norm, but if the semi-norm of a vector is 0, then the vector is not necessarily 0. It's the only difference. And these spaces are called locally convex vector spaces. For instance, if you work with a space of smooth functions, that is infinitely derivable differentiable functions, then you need a countable set of semi-norms. You need one for each derivative. And there is, since it's infinitely differentiable, you need an infinite number of derivatives. And if you work with a space of test functions, then you need still more semi-norms. In fact, the set of semi-norms is uncountable. So you need a very large number of semi-norms. And now when you, what is the connection between the definition by Gatto and the one that we use in physics? It is given by this expression, that is the Gatto differential of f at u in direction v is what we call a functional derivatives with respect to u of x multiplied by the function v of x. And as a consequence, the functional derivatives are usually distributions and not functions. And this will bring a lot of problems. Now, this definition is not enough in the sense that if we have only the existence of such a functional, of such a ghetto differential, that then many crazy things will happen. And so one of the first works done by Kasia Reisner was to add some hypotheses that are necessary to get a usable functional derivatives. And so she found that there are more than 20 different additional hypotheses. And among these more than 20, she found out that only one may be useful or may have the property that we need. And what we did together was to show that indeed the one that she selected is the correct one. And this definition of essentially what is a continuous derivative was done by André Bastiani in a PhD thesis at the Sorbonne University in 1962. And now André Bastiani is a professor at the University of Picardie. And so the definition, the precise definition is the following. It's called Bastiani differentiability. So I give you, it's a bit mathematical, but still it's really crucial. What you need is that if U is an open subset in a separated locally convex space E, and F a map from U to a separated locally convex space F, then F is Bastiani differentiable on U if F has a Gateau differential. So that's what's the previous definition at every U in the open set, and the map and the following map is continuous on U times V. So if you take this definition of a continuously differentiable function, then everything that we do in physics textbooks has a mathematical meaning. The chain rule holds, the Leibniz rule is correct, you get linearity in V, the fundamental theorem of calculus is okay. Moreover, if you take mth derivative, you obtain something that can be considered as the m-point green function. And there is an equivalence in the sense that a function is Bastiani smooth if and only if all its derivatives are continuous in the sense of distribution. So you get an exact identification between the mathematical concept and the physical one. Now, I would like to come back to what Eric discussed about the Hadamard product. So the point that was stressed in the previous slide was the fact that the functional derivative is a distribution. And the point is that distribution cannot be easily multiplied. Even very simple distributions. So the standard example is the step function. So the step function is the function which is 0 for x smaller than 0 and 1 for x larger or equal than 0. So it's clear that as a function, the nth power of theta is equal to theta. Now, to such a function, you can associate a distribution, which is just the integral of the function by the test function. And we know that distributions are infinitely differentiable. And we also know that the derivative of the step distribution is the delta distribution. So assume that you can multiply step distribution and you have the same equation as for a function. And assume that the Leibniz rule holds, then you can take the derivative of this equation and you get that n times theta to the power of n minus 1 delta is equal to delta. And by using this equation, you obtain that n theta delta is equal to delta. And this is true for any n. So you see that this equation cannot hold. And as a consequence, you cannot define the product, the powers of the step distribution. And this power is in the sense of a Hadamard product. Now, still there are distributions that can be multiplied. And there is a classical theorem of Fourier analysis, which says that the Fourier transform of a product of two distributions, when the products were defined, is equal to the convolution product of their Fourier transforms. So there is a way to define the product of distributions by just taking the convolution of the Fourier transforms and then taking the inverse Fourier transform. And for instance, if you take this distribution, U plus, you can see that its Fourier transform is expressed in terms of the theta distribution. And you can see that convolution product is well defined. So this integral is finite. And so you can define the square of the Hadamard square of the distribution U plus. Now, it would be nice to know, to have a simple way to know when you can multiply distributions or not. And this simple way was expressed by Hadamard in the 70s using the concept of a wavefront set. So the idea of the wavefront set is that so distribution has a singular support. There are points where the distribution is not smooth. And for each point of the singular support, there are directions in the Fourier transform where the Fourier transform does not decrease fast enough. And so they are represented by this arrow. So I take the Wightman propagator. Wightman propagator is the vacuum expectation value of the product of the scalar fields. So they are relativistic fields, phi of x times phi of 0. And this Wightman product is called d plus of x. It's a distribution. The singular support is the light cone, the one that is written in blue. And for each point of the light cone, there is one direction in the Fourier transform, where the Fourier transform does not decrease fast. And this is given by this arrow here. And you see that the only point where there is more than one direction is at the origin where there is a cone. And because of this specific structure and because of a theorem by Hadamard, just by looking at this wavefront set, you can see that the powers of the Wightman propagator are well defined. So you can define the nth power of d plus. Unfortunately, what we use in quantum field theory or in field theory is the Feynman propagator. And so the wavefront set of the Feynman propagator has the same singular support. It's again the light cone. But at the origin, you have the Fourier transform is non-decreasing, non-fast decreasing in every direction. And because of this, you cannot define the product of the Hadamard product of Feynman propagators, and you need to renormalize it. It's the origin of the renormalization in quantum field theory. So now, can we define functionals of green functions? So this was done. So the first point is that green functions are distributions. So in principle, you cannot define even powers of them. And also the space of distributions is too wide to define functional derivatives with respect to them in a mathematical way. So what was done by Kasher-Eisner and Friedenhagen and others in the case of quantum field theory was to define the same functional, but in terms of smooth functions. Then you can define derivatives and so on. So you compute the functional derivative of your functional, and you compute the wavefront set of your functional derivatives. And then you can check that this wavefront set is compatible with the wavefront set of the green function that you want to use. And this defines perturbatively f of g. And if you can prove that this expansion converges, then you have a non-perturbative definition of f of g. Now, this method was used by Friedenhagen, Kasher-Eisner, and others to define relativistic quantum fields on curved spacetimes. But this, at some stage, to obtain the complete theory, they still require some renormalization. Now, we don't know whether this works for functionals of non-relativistic green functions. because the wavefront set of non-relativistic green functions is more complicated than the wavefront set of relativistic green functions. But still, this wavefront set was defined by Louis Boutet-de-Monvel, but we didn't investigate this in detail. So I may end the talk with some bibliography of the work that we did, and also the book written by Kasia Reisner. I thank you for your attention.
Okay, so thank you very much. So, okay, so we have a question in the chat by Antoine about the Gateau derivatives. Maybe you want to ask it now?
Okay, so it's just so why do you use Gateau derivatives and C-infinity functions rather than Fréchet and Banach spaces, maybe with the use of several spaces or spaces like that?
Precisely because the spaces that we use are not always Fréchet. That is, in the sense that since we use so the real space that we need is the space of distributions with a specified wavefront set, and this is not a Fréchet space. It's
okay, my question is, why do you need this space rather than more standard Banach spaces?
Why I need this space? Because as you saw, I need distributions, and I need to define wavefront sets on these distributions. And space of distribution, the space of distributions itself is not a Banach space. And the space of distributions with a given wavefront set is also not a Banach space. That you need more than one norm. It's not because we like complications, it's just because even smooth functions are not Banach spaces, and test functions are not Banach spaces. That's why we need an infinite number of semi-norms and not just one norm, as in a Banach space.
Okay, so I think Mark wanted to ask another question. Hello, Mark Dvorak. No, he's not here.
Can you hear me?
Yes. Okay.
Okay, good. My microphone is having some trouble.
Okay.
Yeah, I wanted to actually revisit the same question. So now Lucia has responded, I think, to me, if I consider it as a function of times or its frequency Fourier transform. I don't think that helps. So as I understand it, the problem you had set up had a time-independent Hamiltonian in the first part of the talk. And then there was this H of Z.
Mm-hmm.
And I know that Dyson's equation looks this way. But what I don't understand is where this frequency dependence comes from, because it seems like the problem was set up differently. So of course the Green's function is a function of 2 times or a frequency. But I think the way that this was set up, the Hamiltonian itself is time independent.
So it's the question for Eric.
Yeah.
Yes. So indeed, the n-body time, the n-body Hamiltonian is time independent, but in the Green's function, in the interacting Green's function, what you get is a reduced representation of this the resolvent of the n-body Hamiltonian, and then it's like in Feshbach-Schur approach, if you want. You have a big matrix, and then you focus on you focus on a small part of the information on this big matrix, And when you solve an eigenvalue problem, then the reduced eigenvalue problem depends self-consistently on the eigenvalue. Okay, so it's a bit similar.
Yeah, that I understand as well. I guess this is a little bit mysterious to me because no downfolding is part of the definition of the problem.
Okay, so we have a question from Lucia. Can you ask it?
Okay, now I don't know to which thing you refer, because I wanted to ask a question to Christian.
Yeah, okay, so go.
And I could also comment on Mark's question. So
yeah, please.
Yeah. As you prefer, go ahead. You can do the two of them.
Okay, then I will ask my question to Christian and comment to Mark first. You can look at this like an embedding problem, right? So as Eric said, you have the full many-body Hamiltonian, and then you can write it. You can write the whole problem in the basis of excitations, which are all possible excitations of the many-body system. And then your interacting Green's function is just a matrix element with a specific excitation, which is starting from the ground state, adding or removing one particle. So it's a specific element of the whole inverse. And so you can do like in an embedding problem, and out comes the frequency times self energy. You understand this?
Yeah, I understand. But for example, in the Lyman representation, there's nothing like this. There's just the amplitudes and the poles, and there's no kind of like downfolding.
Absolutely. But that's a completely different representation. The Lyman representation doesn't know anything about the self energy.
Yeah,
right?
this is so this is the part that I struggle with, because there's a jump, I think, that happens, and
Okay,
well,
if you want, we can discuss this separately, maybe.
yeah, sure. Thanks for the reply.
We can discuss it separately. So my question to Christian is, if you consider the Green's function not in Fourier space, not as a function of frequency, where you have the poles, but as a function of time differences, do you still have a problem then with all your functional derivatives and so on?
Yes, in fact, the thing as we formulated it was in the space-time framework. So
where does the problem then come from? Because
from the fact that the Green function,
the functions of the Green's function, or
no, but even in the non-relativistic case, the Green function is singular for t equals 0, for when the difference between 2 times is 0.
Yeah, so it's the theta function part that worries you. The step function part.
Well, it's the fact that you multiply. It's a time order product, so you have a theta function times a certain product.
Yeah, and it's a theta function part that worries you.
Multiply, yeah, plus theta of minus t times it's this theta function.
It's just a theta function. Okay, yeah, I understand. Okay.
And that's you don't have that problem in if we could use only the product, but the product, the fact that you multiply the product of fields by a theta function brings the.
So if we made a functional not of the Green's function, but of the two parts of the Green's function, the electron and the whole part, explicitly. But
the point is that since we used functional derivatives, we need Green functions which are symmetric in the time space-time variables, because of the second derivative, you can commute when you.
Yeah. No, I didn't want to throw away one part. I just said we could try to make a functional of not of G, but not of G greater, G lesser, but without theta function, just electron and the whole part. And then, of course, we would have mixed functional derivatives and everything you want, but maybe this could circumvent the problem.
Yes, that might be a good idea.
Okay, yeah. So we have also a question from Simon on convergence of the perturbation expansion. Can you ask your question?
Yeah, well, I just remembered this this argument due to Dyson, how he showed or at least had an argument that in electrodynamics that the perturbation expansion is asymptotic, that the alpha equal to 0 is a singular point. But I don't think he even said himself that this wasn't a rigorous proof, that this was just an argument. So I was wondering if there is any rigorous results about the nature of the interaction strength of 0, whether it's a regular or singular point, and whether the interaction is asymptotic or convergent.
Yes, so the argument by Dyson was that if you change the sign of alpha, then you obtain you obtain a system where electrons are repulsive, and so there is no bound state, and so there cannot be any analytic connection between those two systems. And
right.
And so, but there is no proof that quantum electrodynamics is not convergent, but there is certainly less proof than it's convergent. So we don't know for the moment.
So also the theories that you and Eric were talking about, where you had non-relativistic interacting theories with the U interaction, there are no rigorous results whether the U equal to 0 is a singular or regular point.
No, not that I know of.
Okay, thank you.
Same here. Yeah.